There is one additional probability topic that I want to cover, and it is the use of probability tables. More specifically, I want you to be able to make intelligent statements about probabilities when you're looking at a little probability table like the one you see here. I sampled 329 students, and let's say for the sake of argument, it's a nice random sample. We've talked about what random means, right? I sampled 329 students and I asked them a couple different questions. Probably asked them a whole bunch of questions, but here are the questions that pertain to this particular table. I asked them, what year in school are you? Are you a freshman, a sophomore, a junior, or a senior? And then I asked them, are you employed? Do you have a job, whether it be part-time or full-time? I didn't really differentiate. I just said, are you employed? Yes or no. And this little table puts those two variables together. And so you can see there are 28 freshmen. Let me come over here. Where is my cursor? There it is. There are 28 freshmen. There are 175 sophomores, 102 juniors, and 24 seniors. There are, I'll come over here, 246 students that were employed. There were 83 students that said no, they're not employed. Grand prize total of 329 students. Now, what I want you to be able to do is answer some basic questions about this table. And let me, before I even start, let me just tell you that there are different probability rules that you can look at to help you with some of these probabilities if you want. The probability, the additive probability, there's a Bayes theorem, there's a conditional probability. What I'm going to suggest to you is that those probability rules, while they work, they make it more difficult than it needs to be. The acronym KISS, right? Keep it simple, student. That's my version of KISS. Keep it simple, student. Goes a long way in solving probabilities. Let me give you a for instance. What if I ask the question, what proportion of my students are upperclassmen? And whenever I'm asking questions, I have to try to use language that I'm sure everybody knows. An upperclassman is kind of an older terminology, and it's not used as much as it used to be. But an upperclassman is defined to be somebody who's a junior or a senior. Okay, if you're a junior or a senior, you're considered an upperclassman. I guess freshman and sophomore, I don't even know if this is a term, but I'll call them lowerclassmen. So what proportion of my students are upperclassmen? And so you can see in this little chart right here that that would be these two groups, right? What proportion are juniors or seniors? And you can see that there's 102 juniors, there's 24 seniors. So we're just going to add those two things together. That's 126 out of the 329, and that's my answer. That's a good or problem. It's a probability one or the other or both. Now there is no both in this case. What do you mean by that? A student can't be a junior and a senior at the same time. So I can just kind of add together the junior and the senior. And there's an additive rule of probability that's perfect for ORs that says take the probability of the first group, take the probability of juniors, add to them the probability of seniors, and subtract the probability of both. There is no probability of both. Junior and senior, those two outcomes, based upon some terminology we learned in a previous lecture, junior and senior would be considered mutually exclusive outcomes. Right? They cannot happen at the same time. When you're doing OR probabilities and you have mutually exclusive outcomes, you can just add the probabilities together. So this is an OR problem where I'm just taking the 102 and the 24 and I'm adding those numbers together in the numerator and then dividing by the denominator. Now look at this next question. So let's go, whoops. There we go. Find the probability of randomly selected student has a job. So if I go over here to my table, I'm looking at these guys right here. Or is a freshman. And so now I'm going to look over here. And so that's a really lousy arrow, but you get the idea. It would be really nice if you say, well, I'm going to take these 246 and I'm going to take these 28 and I'm going to add them together. And that's a really good wrong answer. In fact, I'd go so far as to say that's the best wrong answer. Now, why is it wrong? Well, these 246 take these 16, take these 131, take these 81, and take these 18 yeses and add them together. That's where the 246 comes from. These 28 freshmen take the 16 and the 12 and add those together. Can anyone see what's wrong here? If I add those numbers together, why would these guys get counted in twice? Because they're already part of the 246, they're already part of the 28. And so what I need to do, I'm going to circle a whole bunch of numbers here. I'm going to take these 246 and then I'm going to take a look. There's a terrible, my mouse. And I'm going to add those 12. And that's how I'm going to do the math. That's how I did the math. 246 are the yeses. Then I'm going to look around and for other freshmen, the freshman knows. Now you could, if you wanted, rather than do the math this way, I'm going to give you a couple options here. You could take these 28, which would be these guys, and then add these folks, right? You could take all the freshmen and add the yeses that are not freshmen, the 131, the 81, and the 18. You're going to get the same number. You could, if you really wanted to be weird, you could take these three things here, which aren't part of it, and subtract them from 329 and get the same 258. The additive law of probability says to take the probability of yeses, take the 246 over 329, add to it the probability of freshmen, add to it the 28 out of 329, and then subtract the probability of both. Subtract the 16 out of 329, and that'll get you the same 258. Doesn't matter how you get there. The point is, there are lots of ways of getting to the right answer. You need to figure out the way that makes the most sense to you. There's not a right way or a wrong way. There's just your way. And as long as you can consistently get to the correct answer your way, then that is your right way. What if I asked, what proportion are sophomores or are no's? Sophomores or no's. Now, this case, let's see, I'll come and get a different color ink. Sophomores and no's. Now I'm going to be looking at these 83, right? Those are my no's, and I'm going to be interested in these 175, but I got to be careful because, again, there's these guys here that would get added in twice. So I would take it and say I would take the 83. I would go across the no's because there's more of those. I'm going to just kind of put a line through them. I would take these guys. That's 83, and then I'd have to add in this 131 up here. And so if math's doing me right, I'd say 214 out of 329. You got to figure out what works for you. Those are the OR probabilities. OR tend to be a little bit more thought-provoking. Let's take a look at a end problem. What proportion of my students have a job and are juniors? So have a job and are juniors. In order to be in the OR, you need one or the other or both. To be considered as part of the AND event, you need both categories. So they need to be yeses, that's have a job, yeses, and juniors. Well, there's just these 81 right here. And I went backwards. Let's try that. There we go. 81 out of 329. I love my cordless mouse, but sometimes it doesn't love me back. 81 out of 320. What proportion of the students are freshmen and have a job? Well, that's going to be 16 out of 321. Or 329, excuse me, 16. Freshmen and, how about junior or have a job? Okay, so I'm mixing and matching my ands and my ors. Junior or have a job? Well, again, we'll look at the have a jobs. I got those 246 still, but now I'm going to add 21 to the mix now. So it'll be 267 out of 329. And so far we've looked at some ors, we've looked at some ands. I'm considering in each of these questions all 329 of my students. Another way of saying that, going back to the prior discussion, I'm considering the entire sample space, the OR questions, the AND questions, considering all 329. Got one more to look at with you in this. Given that a student works, what is the probability they are a senior? And again, I mentioned earlier, there's different types of probability things you can find. Additive rule of probability. This would be a conditional probability because I'm telling you, and this is the way I typically word it. Look what I have here. Given that a student works, think about what that's saying. I'm telling you that they're yeses. Are you employed? Yes, I am. Given that we know yes, what that means now is I'm not going to consider the no's. I'm only going to consider the only part of this little table that I'm interested in is the yeses here. And so it's almost as if you could come in here and you could say, you know what, I'm not going to consider the no's. We're not going to look at the totals. We're not going to consider the entire sample space. Sometimes this is referred to as restricting the sample space. I'm only going to consider the part I know about. Given that a student works, of those 246, what's the probability they're a senior? Well, that makes it pretty easy now, doesn't it? 18 out of 246. All right, let me clear this screen. All right, there we go. Given that they're a senior, let me flip them around now. Given that the student is a senior, now what part of the table are you looking at? Are you considering all 329? I hope not. Given that they're a senior, what is the probability that they work? So I got the same two events. Student works, senior, except I'm flipping them around. Given that they're a senior, what is the probability that they work? 18 out of, this time it's going to be 24. Given that they're an upperclassman, what is the probability they don't work? So I got to go get a pen again. I had the eraser out. Let me get a pointer here. Given that they're an upperclassman, given that they're in these two columns here, what is the probability that they don't work? So the denominator now is going to be the 102 and the 24. That's 126. 27 of the 126. Given that they don't work, now we're looking at these 83. What's the probability they're an upperclassman? 27 out of the 83. There's some grand formulas, but I'm telling you, they tend to make things more complicated. If you want, check out the text. It'll be happy to go through and talk to you about the conditional law of probability. Use common sense. Use as much common sense as you can muster. Think about what you're working with. Here's what I'll tell you, though. These conditional probabilities, I'm going to use a phrase. I'm going to say, this has occurred. The challenge that I say, it always amazes me, but I'm going to tell you what's going to happen, and we'll see what happens this semester. When I go back to this question, what proportion of my students have a job and are juniors? Students are going to try to make this a conditional. They're going to try to make this say, given that the students has, that's not what this says. This says what proportion of the 329 have a job and are juniors. This says, given that a student works, don't look at all 329, just look at the 246 students at work. Now, what's the probability they're a senior? You have to be told that this information is true. We know the student works. Now, what's the probability they're a senior? What is the probability that they're a senior and they work? 18 out of 329. Given that the student works, what's the probability they're a senior? Now it's 18 out of 246. Different wording, different. There's a nuance there. You got to see it. And that's what I want you to be able to do. I'm going to concentrate your probability effort mainly on these tables. You have or questions, you have and questions, you have conditional probability questions. Hopefully that makes sense. I'm sure there's a quiz that you can take that'll give you some practice. There's some homework problems in the textbook that'll probably give you some good examples of these tables as well. Make sure that you can answer probability table type problems because you're going to see them again. When you have questions, you know how to get hold of us. So long.